Yeah, thanks so much everyone for being back here. And yeah, day 2 in week 2, so that's pretty cool. The engagement on your personal Discord groups has been outstanding. Just thought I'd comment on it. And yeah, organizing your annual meetings afterwards to go through everything. I think that's exactly the point of the boot camps. And yeah, so keep that up. If you're not doing that, it'll be awesome if you can start that, or just get the chat going on your individual groups. Yeah, so that's really, really cool. And just on that, a couple comments. Engagement is what really makes kind of the cohort stick together and the community vibe. Yeah, so please just keep engaging, keep asking questions during Lawrence's presentations. Yeah, enjoy the session. I'll keep letting people in. If you got anything, just ping me. Always keen for a chat.
Thanks, Jake. Hey, everybody. Yeah, good to have you here. Just a small point, I put a new poll on the Slido to ask about the homeworks that you've completed. So please fill that in so we know then how many people have finished the homework, and then we'll go through the answers for that. That's great. Okay. So today we're going to take a break from Solidity itself and do a more theoretical lesson, and we're going to cover zero knowledge proofs and associated technology. And the reason for this is that well, one is that this may be useful for you when you're doing your projects, you're deciding what to do. Having an idea of what technology is out there that you can incorporate into your projects could be useful. And then the other thing is that later on in the course, we'll be talking about scalability and things like layer 2 solutions. And one large aspect of that is a dependency on zero knowledge proofs. So I want to go through some of the background to that before we get to the scalability. Now, unfortunately, this is going to just be an overview. We don't have time to go into this in much detail, and it is a shame because this really is one of my favorite topics. If you are interested, looking at this in more detail, I've got links in the notes anyway, but also we ran a course. We had a 4-week course on zero knowledge proofs, and so if you're interested, please speak to Encode, and maybe we can organize another one of those courses, because it is a really interesting topic, and it's extremely hot at the moment. There's a lot of people doing a lot of work in this area, so yeah, it's fascinating. Okay, without further ado, I shall share my screen and we can make a start. A couple of quotes to begin with. I think the context is important. A lot of these technologies are around issues like data privacy and giving users control over their data, and not allowing large institutions to control their data. But a caveat in that second quote is that few people really understand zero knowledge proofs. And they are often seen as quite magical, but also a cure-all, a kind of a magic bullet that would fix anything, which is not the case. And people may sort of see them in the same way as things like machine learning. They don't fix everything. They are quite specific in what they can do, and we will cover some of the ideas of what they can do today. But yeah, please do be aware of that. They're not a cure for everything. They're not the solution to everything. So to start off with, I just want to introduce a little bit of maths. So not for you to spend much time on this. It's really just to give you an idea of some of the terminology, because if you start looking at this area, you will start to come across some terminology that you may not have come across before. And even though a lot of the background maths that you need is not too difficult, it may well be new to you. It's not the kind of maths that you would necessarily do at school. So it's worth just to mention some of the terminology. And one of those is this letter Z, the symbol Z here, which denotes a set of integers. And when we're doing cryptography, we very often do this using integers, and the elliptic curve cryptography we use in blockchains is all about using integers. So you may well see this symbol if you talk about elliptic curves, or definitely when you're talking about zero knowledge proofs. Fields we'll come on to in a moment, and when we're doing using things like elliptic curves and doing some types of cryptography, we often use modular arithmetic. And this, some people describe this as clock arithmetic, because the idea behind it is that you have a limited number of numbers that you use, and as you get to the maximum number, then you wrap around and start again. So this is similar to how clock works, the fact that you get to 12 and then you start again you go over to 1. So a lot of the mathematics involved in cryptography is modular arithmetic, and you've probably come across this anyway in programming, using a mod operator. So there's some examples here. So if you're looking at 3 as your sort of maximum number, then 25 mod 3 is 1, and similarly, 15 mod 4 equals 3. And the remainder, this value 1 or the 3, is always positive. Just something to bear in mind. If you start with negative numbers, the remainder you get is always positive. That's the way you work it. And then, I said I'd come up to fields, and these are the basic things that we use when we're doing cryptography, and we're doing elliptic curves, and when we're doing zero knowledge proofs. And fields are kind of an abstract concept in maths, which what they are, they're quite simple if you just take them at face value. And what you do is you say, we're going to do our maths, but we're only going to use integers, and then we're going to work out some special rules for how we do some operations. So we're going to restrict the types of operations that we do on our integers. And when we do that, we choose 2 operations that we're allowed to do. So we're going to call these addition and multiplication. And then also we're going to have a maximum integer. So we're going to be using modular arithmetic, and usually this maximum value is a prime number. And if we set it up like this and we choose the prime number in the correct way, we find that there are certain properties that we get. And if the elements and what we're doing follows these properties, then we can say this is a field. Now, I've just listed out the properties here. You don't really need to think much about them. They are fairly standard kind of things to do with arithmetic, but it's just, you will come across this notation, this idea of a field when you're doing cryptography, and it's worthwhile knowing what this means. It's just an abstract concept. It's just the fact that you're restricting the set of the numbers that you're using. You're restricting them to integers, and you're restricting them to having a largest number, and then you define the operations that you do on those in a particular way. If you want more details about these, then there's some links there. You can try out doing operations on fields, and you can read more about them. You may also come across this term, the order of a field, and that is just the number of items in that field. So if we're talking about integers, that's the number of integers in the field. So if our field had, if there were 20 integers in our field, the order of the field would be 20. Now, in the cryptography that we do, and with zero knowledge proofs, we have very large fields, but they are finite fields. So there is a maximum number, and it's often the order of, it's often roughly 2 to the power of 250 something. So as you understand, that's a very large number of elements in the field. Okay, so that's just a little bit of background terminology that you will come across when you're if you dig into this area a little bit more. But I'll go now on to a more intuitive idea of what zero knowledge proofs are. And there is a difficulty when talking about zero knowledge proofs, because it's not difficult to give sort of intuitive examples of what a zero knowledge proof is. And that's kind of one extreme. And then the other extreme is, reading the research papers about proofs. And there's very little kind of in the middle that explains them in sufficient detail that you get an idea of how they work, but without getting completely bogged down in the detail. So I'm going to start off with an intuitive idea, and we can go into a little bit more detail. But as I said, it would take quite a few lessons to go into this in much detail. And so we can't go into a lot of detail, unfortunately. But there are two aspects to a zero knowledge proof. And often we may only use one of these aspects when we're using the zero knowledge proof. But the first one is that this is a proof of something. Usually it's a proof that somebody knows a particular value or a particular secret. And then the second part, so that's the kind of the proof of knowledge part. And the second part is the zero knowledge part, which means that you can prove this. You can prove to someone that you know a particular secret. But in doing this proof, in demonstrating that you know it, you do not give away any other information other than that you know it. So the person who is checking whether you know it doesn't find out what it is that you know, and they don't find out any other information other than the fact that you know this particular thing. And usually there are 2 or 3 actors in a zero knowledge proof system. The creator is optional, really. Often that's the prover as well. But the main 2 actors are the prover and verifier, and we tend to call these Peggy and Victor, similar to sort of Alice and Bob. And I'll go through an example now of what a zero knowledge proof is like to give you some intuition of what is involved. And one of the nice examples is the idea of a colorblind verifier. So this is an example where we imagine we have a verifier who has a red and a green billiard ball. And because of their color blindness, they cannot distinguish between these 2 balls. And that person, that's the verifier, that's Victor. And the prover can distinguish between these 2 and knows that one is green and one is red. And the prover wants to show to the verifier that not only is there a difference between these 2 balls, but they can tell the difference. So the way that they can attempt to demonstrate this is that they ask the verifier to take the 2 balls in their hands and to show them to the prover. And then they will hide the balls behind their back. And then the verifier can choose to swap the balls over or not. So it's entirely up to the verifier whether they swap or not. But they will choose to do that. And then they will show the balls again to the prover, and they will ask the prover if the balls have been swapped over. So the first time this happens, we assume that the prover is going to be telling the truth. It's in their interest in this case for them to tell the truth. And so the verifier will show the balls to the prover, and the prover will be able to say correctly whether they've been swapped over or not. Now, from the verifier point of view, they will probably not be convinced by this. They will probably not be convinced that the prover can distinguish between these 2 balls, because it could be down to chance that the prover could have guessed. They could have just guessed, and it's a 50-50 chance whether they've been swapped or not. So the verifier may not believe that this shows that the prover does know a difference between these 2 balls. So what they would do is they would repeat the process. So they would put them behind their back again, decide to swap them or not swap them, bring them out again and ask the verifier again if they have swapped them over. And if they do this the second time and the prover again correctly says whether they've been swapped or not, then if this was down to chance, then it's unlikely that the prover would get this correct. There would be a 1 in 4 chance, but it's still possible. It's a small chance, but it's still there. And so the verifier could just keep repeating this process, and each time they repeat the process, the chance of the prover being able to guess correctly that they've been swapped goes down to the point where it will be insignificantly small. So after going through this maybe 10 or 20 times, the verifier would likely be convinced that the prover does indeed know that there is a difference between these two balls and can distinguish between these two balls. So what has happened here is that the prover has proven to the verifier that they know a particular thing. So that they've shown that they know that the balls are distinct. And also there is a zero knowledge aspect to this because the verifier hasn't gained any other information during this process other than that the prover does indeed know that these two balls are distinct. So there is a zero knowledge aspect also. They have learnt from this. So they've learnt nothing new from this. Okay. And then this process of repeating it is then called an iterative proof because we go through a number of iterations, and each time we do the iteration, the chance that it could be the prover could be just guessing goes down by a half. So that's one example. Another one I particularly like is based on the Where's Wally books or Where's Waldo, I think in the US. And this is where we have a picture of a great many people, and then there is one person within that picture who is dressed distinctively. And the point of it is to find that particularly distinctively dressed person, which is Wally. And you can imagine here, Peggy and Victor are looking at this picture, and Peggy finds Wally and wants to prove to Victor that she knows where Wally is in this picture. But maybe she thinks that if she points out Wally, then Victor is also going to say that, yes, he knew that Wally was there all along, when indeed he didn't. So Peggy would want to be able to prove that she can find Wally without Victor finding out where Wally is. And a way to do that, this is a very physical zero knowledge proof, is that you take a very large piece of paper, you cut a hole in it in the shape of Wally, you then position the book underneath this piece of paper, but in such a way that Victor cannot see where the book is in relation to the paper. And then you make sure that the hole displays Wally in the picture. So then Victor can see through the hole that Wally has been found. So Peggy does in fact know where Victor is. But in doing this, she's not giving away where Wally is within this picture. So once again, she has managed to prove that she knows this particular thing, that she knows where Wally is, and she's done that without giving any other information to Victor. That's a kind of a physical way of doing a zero knowledge proof. And there are many other ways. There's one involving Sudoku as well. You can do that by putting playing cards on the Sudoku grid, so you can prove to someone that you have solved a Sudoku puzzle without revealing to them what the solution is. And I've got a link to that there. It's a little more involved, so I won't go through it, but it involves playing cards, and yeah, it also works quite well. And there are many other ways of doing this and many uses of this. And one use, sort of aside from playing games, is to do with computation. It's because it's not just, if we concentrate more on the proof aspect, we can also use zero knowledge proofs to prove that computation has been done correctly. And there's a good example here from Vitalik, who is talking about doing some hashing, but doing it a huge amount of time. So saying we're going to take the word char, we're going to add a number to the end, but do this secretly. We're going to hash this 100 million times, which would take a long time to do. And then we'll be able to prove the output. And what we can do in this situation is to create a zero knowledge proof of this process, so that you can show that this computation, doing all of this hashing, all of these number of times, has been done correctly. But you don't have to repeat the whole computation. You can just give a proof to someone and they can verify that it has been done correctly in a very short amount of time. And the people sort of talk about the idea that, if you had a computation that took hundreds of years to complete, you could do a similar thing. You could have this massive computation that took hundreds of years to complete, and also have a zero knowledge proof of the answer to the computation. And at the end of it, you could present this proof and show that the computation had been done correctly. And the verification of this proof would take maybe a few milliseconds. You wouldn't have to go back through the whole hundreds of years of computation to show that it had all been done correctly, or not. I mean, if it hadn't been done correctly, then the proof would show that it hadn't been done correctly. So zero knowledge proofs are particularly powerful, and they're often used, with the sort of dual aspect. So they may be used just to prove that a computation has been done correctly, and the zero knowledge part may be irrelevant to that. You may not care whether the person finds out any other information, whether the verifier finds out any other information or not. But then there is the zero knowledge side as well, where you're trying to show somebody that you have knowledge of a secret, but you don't want to reveal the secret to them. Okay. So just to answer the questions, for visualizing fields, really, I don't know if there's a way to visualize them other than thinking of just a large set of integers that has a largest number, and that makes up a field. And if you have that set of integers and then a couple of operations, so addition and multiplication, that would create what is called a field. It's just an abstract mathematical concept, and in this case, you don't need to know any more about it than that. The important part of it really is that there is a largest number, and that if you add 1 to this largest number, then you wrap around and start at the beginning. And how do we verify? Well, that's what the zero knowledge proof is doing. That's the kind of the magic of zero knowledge proofs, is that they can prove a massive computation without repeating the whole computation. So that's the other question. Okay, I'll go through a little bit of the history of these things, and it's quite interesting how they evolved, in that they were invented in the mid-80s, and so long before blockchain. And when they were invented, they came out of the area of maths that was about proofs, and they were the authors of the paper were looking not at the proofs themselves particularly, but they started to think about what happens if the prover or the verifier are dishonest. How do we cope with that? And that kind of led them into the area of zero knowledge proofs. So one of the authors, Silvio Micali, he has carried on in the blockchain space. In fact, all of them have carried on in this space, but Silvio Micali is the founder of Algorand as well. So he's sort of carried on with his cryptography in that area. But when it was first brought out, they didn't really catch on, and it took a few years before people started to realize that there was quite an important concept here, and people then started to develop them, but they were quite unwieldy. They were not very practical, and it took a long time before they became practical things, feasible things. And at the beginning of the century, there were more papers coming out about proofs, and there was a landmark paper in 2016 where the Jens Groth at UCL found a way that they could be done in a feasible way, so that they didn't require a huge amount of data or a huge amount of memory. They could be done in a practical way, and that really started off an explosion of their use, because from then people started to be able to use them in blockchains, for example. And this diagram is from the Starkware company, and just shows that there are different families of zero knowledge proofs, and there are different families based on some of the underlying cryptography. And I won't say much about this other than that there is one set of proofs that are called STARKs that are just rely on the fact that there is a hash function. So all that the prover and the verifier need to do at the start of the process is to agree on a hash function. The other types of zero knowledge proofs have different underlying assumptions, such as the discrete log problem with elliptic curves, and the discrete log problem is what we also use for public and private key cryptography and signing algorithms, etc. And so there is a general distinction between STARKs and then the other types of proofs, which are called SNARKs. And Starkware, who invented STARKs, are, in my opinion, really pushing this area ahead massively at the moment. And this area of zero knowledge proofs, in particular what Starkware are doing, I think is one of the big growth areas at the moment within the blockchain space. So as I'll talk about later, they're using this for scalability, and they have a blockchain called StarkNet, which is a layer 2 that is connected to Ethereum, and there is a huge amount going on there at the moment. So if you're interested in this, I definitely recommend people getting involved. It's a massive area at the moment. Okay. But yeah, we'll go on to how zero knowledge proofs are being used. And one of the first ways that they were used in the blockchain space was with Zcash. And then after Zcash, we had other cryptocurrencies that came out doing similar things. And the idea behind them is that when we have a blockchain, if you think about Bitcoin and what that is doing, we have our blocks which are with transactions in them, and we are passing these around the network, and the nodes on the network are there verifying these blocks, and they want to check that the transactions have been done correctly. But in addition to those checks that they're doing, they get additional information. They also get to know what the details about the transaction. So in Bitcoin, they not only can check that the transactions are correct, but they also end up knowing who sent how many Bitcoins to whom. So there's these sort of two aspects, and we don't really think about this much in Bitcoin, that they're getting this additional data. But what Zcash did was to separate this out and say, well, we want to have the cryptocurrency aspect where we're verifying that the transactions have been done correctly, but we want to do it in a way that we don't disclose how many coins have been spent, and we don't want to disclose who sent the coins and who received the coins. And that is what Zcash is able to do. And to do that, it relies upon zero knowledge proofs. And what effectively you have when you have a private transaction in Zcash is that you create a proof that the transaction has been done correctly, but the person verifying that will then know that that transaction is okay, that it is a correct transaction, but they don't get any other information about the transaction. So they don't find out how many coins have been spent or who was involved in that transaction. So it's quite a remarkable use case there, and it brings privacy into cryptocurrencies. And after Zcash, there were a number of other ones. There was the Mimblewimble set of currencies such as Grin, and there's also Monero. Monero started off doing things a little differently, and then they moved over to use zero knowledge proofs. And there are other ones as well. But so that's one of the initial use cases of zero knowledge proofs with blockchain. And then more recently, they have been used to address scalability, and they have made a great deal of difference. And to give a bit of history on this, in Ethereum, well, with all blockchains, it's been known that scalability is an issue. And Ethereum, I can remember from when I started using it, people were talking about scalability and how this was going to be addressed. And there were plans to address this. And one of them, a lot of the research in Ethereum went on to a thing called Plasma, which was what is called a layer 2 or sidechain, which was going to try to address this. But it was a little complex, and it was not, there were some usability issues with it. And then people came up with the idea of rollups. And rollups, and we'll go through this a lot more in a future lesson, but the idea of a rollup is that rather than submitting transactions kind of individually and processing these individually, what you do is you get a batch of transactions all together, and then you, well, on this, if this is zero knowledge rollup, you create a proof that these transactions are all correct, and then you submit that to Ethereum rather than submitting and getting Ethereum to check each transaction individually. And so you get a massive speed up because you're able to batch together the way that transactions are being verified. And as I say, one of the types of rollups is zero knowledge rollups, where you have a zero knowledge proof. There are other types of rollups called optimistic rollups, which have nothing to do with zero knowledge, and I won't go into those here. But on the zero knowledge side, this offers a massive speed up of usability for Ethereum. And if you use one of the zero knowledge layer 2s, such as StarkNet or zkSNARK, then you get this massive increase in number of transactions that you can do. So TPS here is transactions per second. So we're moving from the typical maybe 25 transactions per second that we expect on Ethereum to many thousands of transactions per second. And this has made a massive difference to Ethereum. And it's really addressing some of the scalability issues that we have. And yeah, zkSNARK is another example. So that is one of the great use cases of zero knowledge proofs in blockchain. But another one that I find absolutely fascinating, where they have been used as well, is around nuclear weapons and the treaties around those. And I got these details from some slides from Los Alamos Laboratory in the US. And I think this was actually shown in Nature magazine as well. And they are using zero knowledge proofs and other pieces of cryptography to show that the nuclear weapon treaties are being adhered to. And they do a number of things. And this is one of their slides. Now, I have no idea what Darth Vader is doing in this slide, so I can't tell you what that piece means, but I can explain roughly what the rest of the slide is about. And apparently what they do is they have a lot of information coming in that is to do with monitoring the weapons that they have, so sort of from cameras and whatever sensors, I don't know. And they put this through some sort of neural network. So they're doing machine learning on this and AI on this. And then they get some output. And the way they use zero knowledge proofs with this is they want to prove that the neural network computation has been done correctly. So they can do that. They can create a zero knowledge proof that has been done correctly, but without giving details, necessarily giving details away of the inputs to that. They also can do things. They can take commitments for the inputs to this neural network. So they use hashing algorithms for that. So they can prove that they can commit to what the inputs to the neural network were. And they can also then have some authority that is signing that these inputs and that the model that is being used in the neural network is correct. And all of that then can get bundled up into a proof, a zero knowledge proof to give to a verifier. And so what this proof does is to show the verifier that all of this process has been done correctly, that the computation has been done correctly, that the inputs have been applied correctly, that the thing has been signed correctly, but it's not giving away additional information to the verifier. Okay, so this is kind of, we often see this in that zero knowledge proofs, we can do things called composability with proofs, in that you can gather up a number of proofs and then create a proof of all of those proofs. So you can kind of create a proof of proofs and sort of bundle proofs together. And then we also see them in some of the products on Ethereum. So there is a project called Aztec, which uses zero knowledge proofs to give you privacy in some of the computation, in some of the financial transactions that you're doing on Ethereum. So Aztec, a really interesting project. They allow financial transactions on Ethereum, but they manage to keep details of these transactions private in various ways. And when I'll explain to you the process of creating zero knowledge proofs in a moment, but this is one that we got involved with. They get community together to do a particular part of the setup of the system, and we were involved with that. It's quite a fun process. And then also zero knowledge proofs are used in privacy and identity, and there is a workshop or a lab at Napier University in Edinburgh called the Block Pass Identity Lab, which specializes in blockchain and identity and zero knowledge proofs. And so they also use proofs around issues of identity. So things like a particular annoyance that I have is when I go to a well-known coffee shop and they ask for my name when I buy a coffee. So I never tell them, or I lie about this, because I don't like giving away information more than I need to. And this type of idea is where we could be going with zero knowledge proofs and identity. The fact that you could give out a proof, for example, a proof that you have purchased a coffee, but you don't give away any other information about yourself. Or maybe if you're going to a club, you could give information that you are old enough to go to the club, but you don't give out your date of birth or any other information about yourself. So that's another aspect of how they're being used. Yeah, I've got some general use cases here. You hear about things called range proofs as well. So this is similar to if you had a credit score, you could check that a credit score was in a particular range without giving away details of your credit score. Or you could, with set membership, you can check that a particular passport is not on a list without giving away the passport details itself. We've covered computation, and that kind of comes into the next one of the committed values as well. And also signatures. You can bundle up other aspects of cryptography along with zero knowledge proofs, and then hide what the inputs to the proof were effectively. Okay, so before I go into the next part are the questions. Is there a sacrifice involved with that speed? Not exactly. So, well, there is a sacrifice in terms of it does take a while to produce this proof. You may be able to get through, perhaps you input, I don't know, 10,000 transactions in one batch, but it may take you a few minutes to create the proof for that batch. So there's that, and there's also issues around security and the incentivization of people to create these proofs. There is more on the optimistic rollup side. This is perhaps more. There's more of a drawback in that the proofs there, you don't create a proof for the optimistic rollups unless one is needed. But in that case, it can take up to a sort of a week for these things to be created. So there is that drawback. But I'll cover those in a later lesson when we talk about layer 2s, and we'll go into them in a lot more detail. Okay. So So I've given you kind of a taste of what zero-knowledge proofs are about, and they probably do seem a little bit kind of magical. What I'll try to do now is to go into the, to give you some idea of how they work. And unfortunately, I can only do, I can't go into a lot of detail because there's a lot of maths involved, and it would take a few lessons to go through it all. But I'll try and give you a flavor of what is involved. And I'm going to talk about a particular type of zero-knowledge proof, which is a zkSNARK. So when I was saying earlier about these sort of the being STARKs and SNARKs, this is the SNARK side. And we typically start off when we want to create a zero-knowledge proof system. By the creator, they will have some kind of algorithm, which we're going to call here C. And this algorithm really is a test of the thing that you're trying to prove. So imagine that I was trying to prove to you that I know the square root of a number. So we could write a program to test this. So our algorithm would just take the number that we're trying to find, that we want to know the square root of. So for example, 25. And then it could take the number that I provide when I'm saying I know the number, which would be 5, and then it would square 5. And if that equals 25, then we would return true. So that's the algorithm that the creator creates to form the basis of our proof. And we take that algorithm, and then we need to have a bit of random data, and this random data has to be kept secret, and it's called the lambda parameter. And when or certainly the initial types of zkSNARKs, the way they work, they required this secret parameter. And it was important that this was kept secret, that people didn't find out what this value was. And the reason was that if you know what this random piece of data is that you're using when you're setting up the system, if you know what this is, this lambda value, then you would be able to create false proofs. So you would be able to generate a proof which would look correct, but was in fact false. So the start of this process is to have this secret lambda and our program, our algorithm that is showing what we're trying to prove. And from that, we generate what are called two keys, a proving key and a verification key. And these are not quite the same as the keys we have in sort of public-private keys that we have in cryptography. They are just pieces of data that are then used to in the rest of our system. But these two values are known to the prover and the verifier. And the way the process proceeds is that the prover, Peggy, takes this proving key. She can then take a public input. So a public input is a value that is known to everyone. So in the square root example, this would be the number that we want to find the square root of. So our 25, for example. And then she also takes what is called the witness. So this is her secret, the private value that she doesn't want anybody else to know. So in our square root example, this is the root of the number, the 5. So the prover can take these pieces, the proving key, the public input, or there may be many inputs, and the private, the witness, the value, and from that she can generate a proof. And this proof is intended to show that Peggy knows this witness value that satisfies this algorithm. And then Victor, the verifier, will do a similar process, but he will take the verification key that we've created in the initial setup. He will take the public value, so the 25, for example, and he will take the proof from Peggy. And from those, he is able to check whether this proof is correct or not. He's able to verify the proof. And this function would then return true if Peggy does indeed know the square root of the value that is the public input. So that, in a nutshell, is the whole process of that goes on with a proof. So go back to the start of this and this secret parameter lambda. When this was originally sort of talked about in the research papers, people didn't really think about this very much. But when it was done practically, they realized that this could be a security problem, that you had to keep this lambda parameter secret. And this may be difficult to do in real systems. And so what evolved was a thing called a trusted setup. And this is a way of creating the initial setup of the system, which incorporates this lambda value, but doing it in such a way that this value as a whole is not leaked. So to make sure that people cannot find out what this lambda value is. And the way this is tended to be done is that we do what is called a multi-party computation. So we have a trusted setup which involves a lot of people. And in the Aztec setup, there are many hundreds of people involved. In the Zcash setups, there have been a number of different iterations of this, but certainly they also had one where there were hundreds of people involved. And the idea is that you have a lot of people involved, and each of them has a small part of this secret value. And as long as in this setup, as long as one person is honest, then the whole setup works. As long as we don't have everybody colluding together, then the whole setup is okay, and people won't be able to find out what this secret value is. Okay. On the downside to trusted setups, this is a kind of a lengthy process. It's something that people regard as a setback and a disadvantage to the way that zero-knowledge proofs work. You can argue, and I do argue, that it kind of helps establish your community because you get a lot of people involved, but you probably don't want to have to do that. And it can be a lengthy process. The process for Aztec, for example, took a number of weeks to do this trusted setup. So people think this is a disadvantage to zkSNARKs. Starks, on the other hand, the other type of zero-knowledge proof, don't need a trusted setup. So that's a much easier process to start with. Okay. Now, if you want to try out zero-knowledge proofs, you can do this. There's a project called Zokrates, which allows you to create zero-knowledge proofs on Ethereum and write small programs, and then from those create proofs that can be verified, and the verification is done within a smart contract. And there is a plugin for this in Remix. If you want to try it out, if you click on the plug icon and look for Zokrates, you can activate the plugin, and they within that plugin they talk you through the process, so you can go through the process and try it out for yourselves. And the process it goes through is very similar to what I just talked about, which is that the creator writes a program that describes what you're going to test as part of your proof. It goes through a trusted setup. You get a verification key and a prover key. You can then put in the inputs to the proof, and with the prover key and the inputs, you create a proof. And then with the verification key, you can create a smart contract, which acts as the verifier. So this is one of the advantages of doing this on a blockchain, is that you don't need a person to do the verification. You can have the verification being done in a contract. And then you can take the proof that you created and input that to one of the functions within the verification contract, and it will come back with a true or a false, saying whether this is a correct or incorrect proof. So this was is a great project. When it first came out, it was really the first practical way to do zero knowledge proofs on Ethereum. So there's a lot of excitement about this, and it's worth having a play with that if you're interested in trying it out. Just to delve a little bit more into the theory behind proofs. So I've already said, we have these different types of inputs. So we have some variables which are public and some variables which are private. And there are some requirements that we have of a proof. So from a theoretical point of view, our proof has to satisfy two conditions, really. So the first one is called completeness. And this is the fact that if you have a prover who is honest and they submit a proof to an honest verifier, then the outcome of that is that the proof will be accepted with a high degree of probability. Now, I should say that zero knowledge proofs, the ones we have so far, are probabilistic. So there is a small probability that an incorrect proof could be accepted. But the probability of that is so exceedingly small that it is ignored. And the size of that probability depends upon the size of the field that you use when you're creating your proof. So when I spoke about fields at the start of this talk, I said they were extremely large, and they are. So there's 2 to the 250 elements within them, and it's the chances of one of these proofs being accepted incorrectly is typically 1 in 2 to the 250 something. So it is small enough that it can be neglected. We haven't done that many proofs in the history of zero knowledge proofs, and we probably never will get through that many proofs. It's an exceedingly large number. Okay. The second aspect that zero knowledge proofs have to have is this thing called soundness. And I've written this way as to sort of be an exact statement from the sort of mathematical point of view, but you don't have to worry about all of the terminology here exactly. But it's saying that if you have a dishonest prover, that they will not be able to convince an honest verifier of an incorrect proof. And then this thing about superpolynomial time, etc., that's just sort of putting limits on the amount of resources that the various people have. But you don't need to worry about that, really. It's just saying that if the prover were dishonest, they wouldn't be able to get a verifier to accept a proof. And again, with a caveat that there is this slight probability that I've said. So that's looking at it from the proof side of things. So this is about how you can, proving to somebody that a statement is true, or proving to somebody that a computation is correct. But then in addition to that, we have the property of zero knowledginess. And this is just the fact that at the end of the process that we have, when we've done this proving and verification, the verifier only gains one piece of information. So exactly one bit of information, and that is whether the proof is true or false. They don't receive any other information, and that is the zero knowledge aspect of that. Okay. Now, in the initial one of the initial examples I gave you, when we had the colorblind verifier who was showing the billiard balls to the prover, we had an iterative process. So we had interaction between the prover and the verifier, and that is fine. I mean, that works, but it's a little bit cumbersome. And if we're talking about using proofs in the blockchain space, we don't really want to have that process. We would like to be able to submit a proof and to have it accepted without having to go through a number of rounds or number of iterations. And so you get this distinction between interactive and non-interactive proofs. And the ones we want are non-interactive proofs. And a zkSNARK is a non-interactive proof. We create the proof, we submit it to the verifier, and the verifier verifies it, and that's the end of the process. We only have to do that once. The next point about SNARKs is whether they're succinct or non-succinct. So as I said, when we initially had zero-knowledge proofs, they required a great deal of data, and the proof itself was so huge that it wasn't really feasible to pass around simply. You couldn't sort of submit this to the blockchain easily. So what happened when Jens Groth did his paper in 2016 was he found a way of making these things succinct. So after that, the size of the proofs, and if you do this in Zokrates, you will see this, the proof is just around about 250 bytes long. So it's a very small piece of data that the proof itself. You don't need a massive piece of data for your proof. So this means it's possible then to easily transmit this across a network. And it is still quite astonishing, I think, the fact that you can have this, and you could have a proof that is just 250 bytes long that could be a proof of a computation that has taken many hundreds of years to complete and things like that. It is really quite remarkable. The next two items, they're really just sort of the mathematicians being pedantic about what proofs mean, and one of them is really saying that you're not just proving that something exists, but you're proving that you know that particular thing. So Peggy, when she says she knows the square root, she's not just saying that there is a square root for this number. She's showing that she actually knows what that square root is. And then the idea of argument versus proof is to do with the amount of resources that the people involved have. And again, it's not, you don't need to think, to worry about that so much. It's just there for the mathematicians. And the reason I've given these little items here is that explains what SNARK means. So they are succinct, they are non-interactive, and they are arguments of knowledge. And that's what the initials in SNARK stand for. So yeah, just to go through the process in a little more detail. Actually, before that, I'll just answer some of the questions. So the lambda is required by certain types of zero-knowledge proofs, and it is there to ensure that the prover and the verifier cannot cheat effectively. I won't go into how that is done because it's very complex, but that's what the lambda is for. What's the most exciting application? I mean, the scalability stuff is really amazing. The fact that we can then use proofs to prove that these transactions have been done correctly. I mean, I think that I like the nuclear verification as well. That's really quite a unusual idea, I suppose, but shows that people are thinking of ways that it can be done. Yeah, I think the proofs of computation really are perhaps some of the most exciting ones, but then also the ideas about identity are good as well. Yeah. Okay, so I'll just talk through the process in a little bit more detail to try to give you a feeling for how these things work. So we start off with this trusted setup. So this is the secret value, the toxic waste, the lambda, and this is where the prover and the verifier agree on what the system is trying to prove, and they make some initial setup for that. And then you take your algorithm, say this is a program that you've written, and then you have to put this through a number of transformations. And this is because what we need for our proof, what we end up with in our proof, is just a piece of data. And it's the way the proof works. They're very mathematical. They require us to be able to do a lot of mathematics on various equations, polynomials in particular. But we need a way to get from our initial program, our algorithm, to these sort of mathematical constructs. And so we have to, we go through these transformations. And the first one is to take our program and turn it into what is called an arithmetic circuit. And we start off by simplifying the program. And in Zokrates, this is all done for you. You don't have to do this specifically. It's all done behind the scenes. But this all does happen. So it's the code that you write in Zokrates is then turned, it is simplified and then turned into what is called an arithmetic circuit. And these can be visualized as looking like hardware circuits. And when you talk about them, it's important to visualize them not as a program. So they're not any kind of algorithm and they're not any kind of flow diagram. They're more similar to an electrical circuit, and they consist of a number of gates, addition and multiplication gates. And what happens is you create this circuit, and the circuit involves the input values. So it involves the public parameters to your proof, and it involves the secret witness to your proof. And when you've got all of these values into your circuit, along with all of the details about the algorithm that you're using, we don't kind of do a flow through the circuit, but we can say that whether this circuit is satisfied or not, whether the circuit kind of makes sense, whether this is a valid circuit or not. And I can't go into the details of that. There's a lot of sort of maths there. I wouldn't go into that. But what we pull out of this circuit sort of to go to the next step is what are called constraints. So we're saying that for the circuit to be valid, then various things need to be true. And so we kind of abstract away from the circuit these constraints, and then we use these further on in our proof. And then we do further refinement, and we take these constraints that we've got from our circuit, and we build sets of polynomials out of these, and we manipulate these in various ways. And the end result of these is that we can check that these constraints are all true. And then alongside that, there is some cryptography that is going on that ensures that when we're doing this, that the prover cannot cheat, and that the verifier cannot cheat, and that the verifier cannot find out too much information about the proof. They cannot find out the secret values that went into the proof. But all of that involves a lot of extra steps and a lot of extra mathematics. Okay, so I hope that gives you an idea of sort of how zero-knowledge proofs work. And we don't always need to use SNARKs. There are alternatives. And one of the problems we do find when we're using these things is finding a trusted source for some of the inputs to our zero-knowledge proof. Okay, so that's all I'm going to say about that. I've got some other bits of technology that I want to go through now that you may find useful. Is it important for this bootcamp? I wouldn't have included it if it wasn't important. And so, as I said at the beginning, there are two reasons for this. One is that you may want to use this technology when you're doing your projects, and zero-knowledge proofs plus the technology that I'm about to come on to. And then the other reason is to understand, when we look at layer twos and scalability, is to understand how they work and how zero-knowledge rollups work. Okay. So yeah, the other technology I want to talk about now, I've got a bit of time left. I'll start off with things called decentralized identifiers. And these are in the identity space. So perhaps a similar or an alternative to zero knowledge proofs in that way. But they are a standard, and they're a standard way of describing identity and being able to show identity. And they're called DIDs, I mean decentralized identifiers. They have various parts to them. They have a document and people who can issue credentials to someone with an identity. So what it allows you to do is, for say, you can set up an identity to prove as your identity, and then you would have issuers such as banks or colleges who would be able to give a credential to show that you have maybe you have an account or that you have passed an exam, and these credentials are verifiable. They're called verifiable credentials, and they use cryptography to show that these credentials apply to you. And then you can use these credentials to show to other people to show that you have passed an exam, for example. And the idea behind these is to introduce control over data around identity and allow people to be selective in the data that they show to and give to other systems, and restrict that. And there are a number of companies in the area, some major ones. So I mean, Microsoft are involved, but some of the other big specialist ones are Spherity, Uport. One that we've been involved with is Evonym, and they produce this thing, the Connect Me wallet. If you want to have a look at this is available as a mobile app. You can create a wallet which creates an identity for you, and then you can get people to send you credentials that you can then keep in your wallet, and you can show to other people to prove that you have, for example, passed an exam, or that you have a bank account, or whatever it is. Related to that are KYC providers. I just list out a few here. These are often useful when you're writing real-world applications, and you may well end up wanting to use these in blockchain projects. The first few I haven't used, so I don't know much about them, but they have a number of projects, they're sort of well-known projects there. The last two I've used, particularly Yoti, and they have a phone app that you can use that allows you to prove your identity and go through a KYC process by showing, by using something like your driver's license or your passport, and then doing verification using a video and doing liveness verification to prove that you are a person and not a video. Okay, so that's DIDs, and then there's an aspect of cryptography called homomorphic encryption. Excuse me, and this is really a holy grail of cryptography, in that it allows you to do some very remarkable things. This allows you to do operations on encrypted data, which again you would think would not be possible. If I encrypt some data and add it to some other encrypted data, you wouldn't expect that addition to make sense, but it can do. There are some caveats, and it depends on how the data is encrypted and depends upon the operations that you want to do, but it is possible. And so this is a goal that cryptographers have been working towards, the idea that you could have fully homomorphic encryption, which would mean that you could encrypt some data and then do any arbitrary computation on that data, and that would still make sense. So to give you an idea of what that would mean, if you look at this first diagram, it would mean that the person who represented here in blue could encrypt some plain text data, which ends up then being this green blob of data. And they don't share their key with anyone else. They keep the encryption key for this data to themselves. But perhaps the computation they want to do is particularly complex or expensive. And so they can send this encrypted data off to some third party that has a lot of computational power, for example. So maybe they could send off this data to do some statistical analysis of it. And then this third party would do their analysis and produce another piece of data, which is still encrypted. So the third party would not be able to understand what this data represented. They would just be doing operations on this data. They would send it back to the original person, who could then use their original key to decrypt the data, and they would get back the results of the operation that the third party had done on the data. And that does sound too good to be true, but this is definitely possible. And you can see a sort of toy example of this is given here. If we imagine our encryption scheme is to multiply a number by 2. So we can start off with two numbers, 3 and 4, and we want to perform an operation on these numbers, which is the operation addition. But we're going to send these off for somebody else to do. So first of all, we encrypt our numbers by multiplying them by 2. So we get 6 and 8. We send those two numbers off to a third party, which does the computation, which is to add them together. That comes back to be 14. And then we decrypt that value to get back to 7. So that is the operation done on our unencrypted numbers. So that should give you a feel, at least, for the fact that this is possible. Yeah, I've just described it again there. And one example that is linked to there. So from one of my someone that I knew at Oxford doing this was the idea that you could have medical data that would be sent off to be analyzed in various ways, but it would be encrypted before it was sent, because obviously you don't want patients' details to be sent off to third parties. And so you can encrypt the data, you can send it off to be analyzed, and then you can get back the analyzed data and decrypt it, and that is the result of the analysis. You can also do it actually with Bitcoin addresses, in that you because the hashing process is effectively an encryption, and we can add addresses together. I won't go through this. You can read through it and try it out yourself. But it's a way to create vanity addresses. So if you want a Bitcoin address or an Ethereum address that starts with a certain number, they're doing this this split key vanity mining is a way of doing that. And if you Google, there are sites that will allow you to do this. And for example, you can create an address that starts off with, say, 10 leading zeros or something like that. But that's relying on the same kind of idea of homomorphic encryption. And then another useful technology is called proxy re-encryption. And I came across this a few years ago and then used this in a project. And it's was really championed by a company called New Cipher. And the idea behind this is that if you imagine that Alice has some data and she wants to keep this data secret from the general public, so she will be able to encrypt it with her keys, but she would maybe want to share this data selectively with other people. So what proxy re-encryption allows Alice to do is that she can encrypt the data with her public key, so that only she can read this. She can send this encrypted data off to a third party, a proxy. And this third party, the proxy, is there to do the computation, the heavy work involved in this process. And then if Alice wants to share details of this data with other people, so with Bob, for example, what Alice can do is to create a re-encryption key. So she takes Bob's public key and then she creates a re-encryption key. And what she does then is she can send this to the proxy. The proxy will re-encrypt the data. So it is not the original encrypted data. It's been encrypted again with this re-encryption key, but it is still encrypted. So the proxy cannot work out what this data means. But then the proxy can then make this data available to Bob, who can then decrypt that data with his private key. So it's a way that Alice can get her data to Bob safely via a third party using encryption. But Alice doesn't have to give her key to Bob. So Bob doesn't find out Alice's original key, so the original key that encrypted the data. And in this way, Alice can control who gets access to this data. And this has evolved, and they use it as in a way called threshold re-encryption. I'll just leave that diagram there with you. It just means that rather than having one proxy, you have a number of those, and there has to be some consensus built up before the re-encryption happens. But anyway, yeah, I'll just leave that there. I won't go into that in any more detail because we're running short of time. Okay, and then another useful piece of cryptography that you may find valuable in your projects are things called verifiable random functions. These are used in Algorand, for example, and they are a way of producing a random value as an output, but doing it in a way that can be verified. So we're kind of verifying that the computation used to produce this random value has been done correctly. And we can prove that in a way that doesn't give away the starting point of this is a sort of secret starting point of this computation. So the problem is that if you, for example, if you use a pseudo-random number generator, the types that you used in other programming languages, then you start off that with a seed. If you try to do this on the blockchain, then people would find out what your seed is, and they could work out the random numbers that you will be producing. So verifiable random functions are a way around that. They're a way to produce random values that can be proved to be random, but without allowing some attacker to work out in advance what those values are. And these are used quite a lot in blockchains in different ways. So they can be used in blockchains to find who a block producer is going to be, to find a particular slot for a block producer. You can also use them with the project Chainlink. So Chainlink are an Oracle project. And if you want some random values in your contract, you can go to Chainlink and ask them to produce a random value, and they use VRFs to do that. Okay. Something else you may find, you may come across, the notion of blind signatures. So David Chow invented these, a long time ago, back when he was doing his ideas of DigiCash, really the early days of cryptography. Of the sort of breakthroughs in cryptography. And these are useful, particularly if you're thinking about voting systems. So a nice way to think of them is if you imagine somebody who wants to vote in a system and they want their vote to be verified as having voted correctly. They want to show that they are allowed to vote, but they don't want to give away who they voted for. And so a kind of physical way to do this would be for the voter to put their vote, once they've done their tick on their ballot paper, they put that into an envelope which has some carbon paper in there. The verifier doesn't see this this ballot paper going into the envelope, but knows they've put it in there, and they sign the outside of the envelope, and this carbon paper then transfers their signature to the ballot paper. And then the voter can then take this envelope, including their ballot paper, they can submit that to the people who are counting the ballots, and the people counting the ballots, counting the votes, can then check the ballot paper. They can see that the signature is on there, so they know it is a valid vote, and then they can also then see what was voted for, and then add that to the final tally. So that's the idea of a blind signature, but obviously we don't want to do that physically. So there are cryptographic means to do that. So that if you have some kind of voting scheme you want to do, you can do that with cryptography. And this also is the basis for things called confidential transactions. So Adam Back, who is very involved in Bitcoin, had this idea. We're running short of time, so I won't go through this, but it uses hash functions to do this and to disguise the transactions that are happening. And there is a network that uses this called the Liquid network, and you can see, this is a screenshot from their block explorer. You can see that a particular transaction that has been done, and it is shown that here it is saying it is confidential. So the details of the transaction are not being leaked there. An interesting project, again, I'm not going to have time to go into it, is that is around voting systems and how to prevent bribery with that. And because if somebody is going to vote in a system, somebody could bribe them to vote in a certain way, and then the voter could then show to the person who bribed them that they did indeed vote in the way that they wanted. And if, for example, we have projects like Gitcoin where people are voting to give grants to various projects, this could be problematic because you could bribe the people who are voting to give grants to you. And so I've got details here that you can read through how we get around this. So there's a project called Mackie, which the way this works, the way they get around the possibilities of bribery is that they allow the person who is voting, they allow them to change the key that they are using to vote with and to revoke the previous vote. And this means that the person who is bribing them will never be sure whether they really have voted for them or not, because they could vote for them and show them a proof that they have voted for them, and then later on revoke that vote without the briber knowing. And so this then disincentivizes the briber from bribing people, because they'll never be sure that their bribe is actually being used correctly. But there's some links there to the details of that. Again, I'm running out of time, so I won't go through that. And then other aspects of cryptography you may want to use, other ideas around secret sharing. So if you have a secret, you may want to split that up into multiple secrets, so multiple people are involved. So for example, if you're doing multiple signatures for wallets, multi-sig wallets, that kind of thing, there's cryptography involved that allows you to do that. Now, it's not enough. For example, if you have a private key, if you wanted to share that amongst 5 people, if you just split up that key into 5 chunks and gave each person 1 chunk of that key, that would be a very insecure way of doing it, because effectively people could collude and start putting their key together, and you are reducing, when you reduce the size of the key, you are reducing the amount of effort that would be needed to brute force that key. But there are cryptographically secure ways that you can do this, and one of them is called Shamir secret sharing, which I don't have time to go into, but it's worth looking at if you're interested in that. And then multi-party computation is a similar thing. The idea is that multiple people come together to do some computation, and part of that could be that they have a piece of data that is going to be part of the computation, but they're trying to keep that piece piece of data secret. But the computation as a whole depends upon many pieces of data. And an example of this was the trusted setup that we had with, for example, Zcash or Aztec, where we were doing computation on these random bits of data, the secret lambda, and we didn't want to share what that value was, but we wanted the whole computation to succeed. Okay, so yeah, I'm almost out of time. Just quickly go through the questions. The difference between lambda and the witness. So lambda is part of the initial setup that is done with the prover and the verifier. The witness is the secret value that only the prover knows when they're creating a proof. So we have one lambda that is used to create the system, and then we can create multiple proofs with multiple witnesses to use in that system. KYC, isn't that centralized? Yes, indeed it is. So you are relying on the centralized projects to verify your identity, but it's quite difficult, to find a way around that. It certainly would make an interesting project. Yeah, because the data you get tends to come from centralized bodies such as the government, who issues you with a passport. Yeah. Okay, I'm out of time. So I'll finish there. There's no homework for this because this was just a theoretical talk to give you some background that is going to be useful for you later on. But I hope you found it interesting. It's an absolutely fascinating area, and I really would recommend you look into it in more detail. All right, so that's it. Thank you, everybody, and we'll pick up again tomorrow.